Good morning, class. My name is Dr. Araipur, and this is Pre-Calculus Practice Test number 2, Module 2, which covers chapters 3 and 4. Chapter 3 is about polynomial and rational functions. Chapter 4 is about exponential and logarithmic functions. We start with chapter 3, polynomial and rational functions. The first question is asking about the price demand function. The price demand function of a company that manufactures vats, a large tank or tub used to hold liquid, is given as the function p of x equals negative 5x plus 600. We are interested in finding the revenue function. Revenue function, by definition, is the number of units times the price. So x represents the number of units sold, and the price is given as minus 5x plus 600, and their product is minus 5x squared plus 600x. This is the revenue function. The company's fixed monthly cost is given as $1,563, and each unit of vats cost $10. We want to write the cost function. Now, this really covers the concept of y equals mx plus b, and instead of y, normally we use f of x. In this case, we're going to use c of x that has a fixed cost. We called it the y-intercept, and now we're going to call it the c-intercept. And a variable cost of $10, that is the slope, or m. So c of x is 10x mx plus b, if you will. Let me remind you of that formula. So y, or f of x, is mx plus b, and that's what they are. We want to find the profit function. The profit function, by definition, is the difference between the revenue and cost. So R minus C. So minus 5x squared plus 600x, subtract from it 10x plus 1563. In other words, we would put here minus 5x squared plus 600x. We are going to subtract the cost, which is 10x plus 1563. This is a simple elementary algebraic steps. How many vats must be produced and sold in order to maximize profit? To maximize profit, we are looking at a quadratic function. X must be equal to minus b over 2a. We call y, or f of x, equals ax squared plus bx plus c. X equals minus b over 2a is the x coordinate of the vertex. And in this case, it's a quadratic function. It opens down because of negative 5. So the maximum occurs at its vertex. X is minus b over 2a. And we plug in minus b is 590 and a is negative 5. It results in 59. What is the maximum profit? Well, we go to the profit function and replace the x with 59, evaluate it, and it gives us $15,842. In other words, the maximum occurs when we produce and sell 59 pieces, and the amount of profit is 15,842. What price must the company charge in order to maximize profit? We go back to the price function at the very top and replace the X with 59. And that is the price. We're going to charge $305 per unit. So simply plug into the formula. Question number 2, the polynomial of degree 3 p of x has a root of multiplicity 1 at x equals -6 and a root of multiplicity 2 at x equals 4. P of x passes through the given point 2, 8. Find a formula for it in factored form. Well, it contains the pair, the x equals -6, so that means x plus 6. At x equals 4, that means x minus 4. Going back to the first one, the multiplicity is 1. That means the exponent is 1. The next one, the multiplicity is 2. Therefore, the exponent under parentheses x minus 4 must be 2. So pay attention to this. And what is the leading term and leading coefficient? We don't know. So we call it a. So a times x plus 6. Why x plus 6? Because x equals -6. Times x minus 4. Why? Because x equals 4. Multiplicity of 1, this one has no exponent. Multiplicity of 2, this one has exponent 2. And I hope you realize the degree is 3 right here. So all we need is one more pair and it's given. Here's the pair, 2, 8, which means replace the x with 2, replace the p of x or the y coordinate with 8. So we plug in 2. We get a times 2 plus 6 times 2 minus 4, quantity squared equals 8, and we can find a this way. This is 8. This is a -2. Quantity squared is a 4. We can drop the 8 from both sides and divide by 4, and a becomes 1/4. Therefore, we write p of x as follows, just using this formula, and replace the a with 1/4. P of x becomes 1/4 x plus 6 times x minus 4 quantity squared. Here's the next one. We want to divide using synthetic division. We want to divide 3x cubed minus 2x squared plus x minus 4 by x plus 1. Synthetic division, we have to put the two of them in descending order. And all we have to do, write the coefficients. And if any of them is missing in this case, you have to put a 0 as a placeholder. Therefore, we're going to put number 3, -2, 1, -4. What about this one? We are dividing by x plus 1. So we put a -1 in this format. So we put those numbers in order. And again, any of them missing, we put a 0 as a placeholder. Let's assume we don't have negative 2x squared. Therefore, instead of negative 2, you must put a 0. We are dividing by x plus 1, we put a negative 1. We are dividing by x plus 5, we put negative 5. We are dividing by x minus 1, we put positive 1. So what happens next? We are going to drop number 3. We are going to multiply these two and put it here. 3 times negative 1 is negative 3. And now we're going to add these two. We get negative 5. Again, we're going to multiply this by negative 1 and put it here. Negative 1 and negative 5, their product is positive 5. Add these two. Again, multiply by negative 1, put it here. Negative 6. Add these two, and we get negative 10. Now, therefore, this division will result in the following. We start with x cubed as the first term. Therefore, by division by x plus 1, this must go down. We start with x squared. So this corresponds to x squared, and we go down. So 3x squared minus 5x plus 6. There is no more. What is this? This is the remainder. So we write it as such: 3x squared minus 5x plus 6, and then negative 10, and you divide by x plus 1, whatever your divisor is. You could also write this one as negative and this one as positive, but on purpose, I wanted to keep it in this format so it will be absolutely clear as to what we are doing here. Synthetic division, everybody. Here's the function f of x equals 2x cubed minus 8x squared plus 5x plus 3. We want to list all possible rational zeros of f of x. So what is the rational zero theorem? Rational zero theorem says you write factors of a sub 0 at top, you write factors of a sub n at the bottom, and you write those ratios. Those are possible rational zeros. Please understand, this is a sub n, which means in this case a sub 3, because the degree is 3, and this is a sub 0. So let's write that first. This is a sub n, or a sub 3 equals 2, and this is a sub 0. So factors of 3. What are factors of 3? Plus minus 1, plus minus 3. What are factors of 2? Plus minus 1, plus minus 2. You could write it in this fashion. Factors of 3 are plus minus 1, plus minus 3. For 2 would be plus minus 1, plus minus 2. If you write all of them, you get the following. So plus minus 1 over 1, that's that. Plus minus 1 over 2, plus minus 1/2, plus minus 1/3 over 1, and over 2. So as you can see, we have 1, 2, 3, 4 times 2, 8 possible answers. The next one says find the rational zeros. What that means is you really have to plug in all of them, and whatever gives you 0, when you plug in, remember this is the remainder theorem. The remainder theorem says basically plug in and observe whatever the value is, that is the remainder. So you could put negative 1/2, positive 1/2, negative 1, 1, so on and so forth, and see what happens. It so happened that this is a tedious process, but that is the process to do. And if you plug in, you notice number 3 produces 0. So if I plug in number 3, and I'm going to leave it for you to check it out, we get 0. Therefore, a rational 0 is 3. Now, when we get to 1, you don't even have to continue anymore because this is of degree 3. If I divide by x minus 3, then whatever is left is of degree 2, and we can handle a quadratic equation. So or for that matter, expression to factor. So I highly recommend when you have a degree 3, at least find 1 and then continue with the old method. So we are going to divide this by x minus 3, and I'm assuming, so we want to find the remaining zeros. So we are going to divide by x minus 3, and I'm assuming everybody can do this by any method, long division, synthetic division, either way is fine. And we get to 2x squared minus 2x minus 1, and we are going to use the factoring or the quadratic formula to find the answer. So the quadratic formula will do that because in order for a quadratic expression to be factorable, b squared minus 4ac must be a perfect square such as 1 or 9 or 25. And in this case, it's not. So we use x equals minus b plus minus the square root of b squared minus 4ac over 2a. And we find the following. I hope you realize we are really factoring out number 2. And so x is 1 plus minus the square root of 3 over 2 using QF short for the quadratic formula. If I was to write this next step for you, that means minus minus 2, which makes it plus 2, and then b squared negative 2 quantity squared minus 4 times a, which is 2 times c, which is negative 1. And you're going to divide this by 2 times 2. I'm assuming you can finish the job from here to get to this answer. And again, this is hard to see, but this is negative 1. So if that is the case, how would you write this in a factored format? F of x is x minus 3, and then x minus 1 minus square root of 3 over 2, x minus 1 plus square root of 3 over 2. In other words, if we wanted to rewrite that, and we don't have to, this would become x minus 1 plus square root of 3 over 2. You don't want to do that, I'm telling you. X minus 1 minus square root of 3 over 2. Because the reason you don't want to do that, if you want to multiply them through, it's easier to multiply them just the way it's given, and then multiply by x minus 3. You would write it as x minus 1. Here's, and I suggest you try this. If you want to multiply them through, you would rewrite this as, the first one you would write as x minus 1 plus square root of 3 over 2. The second one you would write as x minus 1 minus square root of 3 over 2, and you use a minus b, a plus b to finish the job, and then multiply by x minus 3. That's why it's a good practice to keep it in this form. Here's the next function. We want to find f of 1 and f of -3. I'm assuming everybody can easily do that. All we have to do is just plug in. So plug in 1 and evaluate it. 1 to the power of 4 plus 2 times 1 cubed plus 22 times 1 squared plus 50 times 1 minus 75. Plug in -3 to the power of 4 all the way to the end. And it so happened both numbers give us 0. And what that means is x minus 1 is a factor, so is x plus 3. That's really the meaning of it. Now, if we were to use rational zeros, we have to use factors of -75, that is your a sub 0, over factors of 1, that's your a sub n, more specifically a sub 4. And it would result in whatever the factors of -75 is in essence. Plus minus 1, plus minus 3, plus minus 5, plus minus 15, 25, 75. There are so many that you have to check. And since we have a couple of them, it really makes life easy. If you were to use the technology, you can go to graph, second calculator 0, or try 1 by 1. We get -3, 1, and we take it from there. Now, by the way, it so happened there's no more, but as long as you can show 2 of them work, I hope you realize the degree is 4. So if we divide by the product of these two, that means the product of x minus 1 and x plus 3, what is left is of degree 2. You can figure out the rest if you were to figure it out on your own. However, the question says, if we know 5i is a 0 of the function, find the remaining zeros. I hope you realize we got 1 here, we got 2 here, we got 3 here. This is of degree 4, therefore we have only 1 more. And we do have this conjugate zeros theorem. If p of x is a polynomial with real coefficients, and if r equals a plus bi is a 0 of p of x, then the conjugate r bar, sometimes they call it z and z bar in many cases, depending on what text you're using. A minus bi, the complex conjugate, is also 0 of a p of x. So if it's 5i, the conjugate is negative 5i, everybody. So we have f of x equals x minus 1 times x plus 3 times x minus 5i, and because of this, x plus 5i. Now, again, if you were to multiply them through, and we're not going to do that, first you would really do this too. I hope you remember a minus bi, a plus bi gives you a squared plus b squared. I've shown you that before. And so we get x squared plus 25. In other words, this comes from the fact that a plus bi, a minus bi, the product is a squared plus b squared, a squared plus b squared. All right. We want to find the domain of this function, and we want to express it in an interval notation. Anytime we have a rational function, the domain is anything that doesn't make the denominator 0. So you set the denominator equal to 0 and you exclude it. So let's do that. We can factor this. We want two numbers. The product is -8. The sum is -2. We end up with x plus 2, x minus 4. This gives us -2. And this gives us +4. That means the domain is all real numbers except those two. Except those two. So here's how we excluded using the interval notation. Negative infinity comma -2 union -2 to 4 union 4 to 8. Notice the parentheses simply mean the endpoints are not included. So that's how we find this domain. Use the remainder theorem to evaluate f of x equals 6x to the power of 4 minus x cubed minus 15x squared plus 2x minus 7 at x equals 2. Simply put, if you plug into whatever the answer is the remainder of dividing this expression by x minus 2. So let's plug in. So 6 times 2 to the power of 4 minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. Of course, 2 to the power of 4 is 16 minus 2 cubed makes it minus 8 minus 15 times 4. And you evaluate it. I'm assuming everybody has an easy time with the evaluation of that. We end up with 25. That is elementary algebra. So what it means that if we were to divide this expression by x minus 2, the remainder would be 25. We want to show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Find the remaining factors. Use the factors to determine the zeros of the polynomial. Well, if this is the factor, then plug in what number should give you 0, because we are dividing by x plus 2, then -2, plug in -2 must result in 0. So let's plug in -2. F of -2 is -2 quantity cubed minus 6 times -2 quantity squared minus -2 plus 30, and they end up giving us 0. This is 4. So what you have here is 3 cubed, which is 27 minus 24. Minus 2. Plus 30. Let's take this question from the top. We want to show that x plus 2 is a factor for x cubed minus 6x squared minus x plus 30. And we want to find the remaining factors. So if we plug in -2, we should get 0. Now, when we plug in -2, this is -2 cubed, which is -8, minus, this is 4 times -6 is -24, plus 2 plus 30, and that results in 0. Therefore, all we have to do, divide this by x plus 2, or by any method. We can do it by long division or a synthetic division. If we want to use the synthetic division, remember, we put these numbers as 1, -6, minus 1, 30, and this one, because we are dividing by x plus 2, we have to put -2. So the process will give us the following: 1, -8, 15, 0, because this is x cubed, This starts with x squared. So 1 times x squared, or simply x squared, minus 8x plus 15. So it's the product of x plus 2 and the expression I just went over. Now this you can either factor, or you can use the quadratic formula on that. So we want two numbers, the product is 15, the sum is negative 8. That's easy to do. Therefore, if we want to use the factor theorem to determine the zeros, this gives us negative 2, positive 3, positive 5. We are given the following function, and we are asked to find the domain of the function in an interval format. First and foremost, anytime you are dealing with a rational expression, rational equation, rational function, if you can simplify, you must. We can factor the denominator into x plus 4 times 2x plus 3. Therefore, x plus 4 cancels out. And so this expression becomes what you see. In other words, it's the same as 1 over 2x plus 3, but x can't be negative 4. As a result of this part, and x can't be negative 4 at x equals negative 4. If you graph this without paying attention to this, so be it in the beginning, and then at this point, x equals negative 4, which means you plug in, it creates a hole because x cannot be negative 4. So that would be the difference between this function and this function, if you will. So these two functions would be identical except at x equals negative 4. So the domain remains the same. X can't be negative 4 and x can't be negative 3/2. I hope you realize that you have to set the two denominators equal to 0, the two pieces, the two factors. And so you exclude the two numbers, negative 4 as well as negative 3/2. We want to find the asymptotes as well as any holes. First and foremost, I discuss the hole because the expression here says x can't be negative 4. Plug in. What happens if you choose x equals negative 4? You get to this pair. This pair is out because x can't be negative 4. Therefore, at this point, we do have a hole. So there is a hole at that point. This is a rough estimate. This is not perfect, but at this point, negative 4 comma negative 1/5, we have a hole. Other than that, graph this one. Basically, graph this one and exclude this pair. Vertical asymptote, you set this denominator equal to 0. 2x plus 3 equal to 0 results in x equals negative 3/2. It is important to note that you can't set this denominator equal to 0. X simply can't be negative 4. That is not a vertical asymptote. That is the result of a hole. And you just set this one equal to 0, resulting in x equals negative 3/2. Let's discuss horizontal asymptotes and oblique asymptotes. So I'm going to remind you of what we have learned. F of x is n of x over d of x. In other words, the numerator over the denominator. This is a sub n x to the power of n all the way to a sub 0. This is b sub m x to the power of m all the way to b sub 0. If the degree of the numerator, that means mn, is less than m, then horizontal asymptote has the equation y equals 0, and this is the case for us here. The degree of the numerator is 0, the degree of the denominator is 1. I hope you realize that. Therefore, we are here. There is a horizontal asymptote, y equals 0. If n and m are equal, meaning they have equal degrees, then the coefficients, the leading coefficients, the ratio of that will take over, and that y equals that number becomes the horizontal asymptote. If the degree difference is exactly 1, in other words, n is equal to m plus 1 precisely, then we can divide using any methodology, long division or synthetic division. It results in a line mx plus b and a remainder. This line y equals mx plus b is our slant or oblique asymptote. So in this case, the horizontal asymptote is y equal to 0. You either have horizontal asymptote or oblique asymptote or none, but you can't have both. So that is the vertical asymptote, and the horizontal asymptote is this y equals 0, the x-axis, everybody, x-axis. You can do a dash line, by the way. Find the intercepts of F. To find intercepts, simply put, set x equal to 0, find y. Set y equal to 0, find x. So x-intercept, none, y-intercept, 0, comma 1/3. Why is that? X-intercept, when y is 0, f of x or y, a fraction is 0 when the numerator is 0. Since the numerator is a number, any number, it can never ever be 0. Therefore, there is no x-intercept. So I'm going to repeat. X-intercept, y equals 0. So you said this one equal to 0. Since the numerator is a number, can never be, there is no x-intercept, but we do have a y-intercept. Set x equal to 0, this goes away and you get 1/3. So set x equal to 0, you get 1/3. And that's the pair, 0, 1/3. Locate at least one point on each side near the vertical asymptotes. When you have a vertical asymptote, in this case 1, it cuts it into 2 sub-intervals. On each side, you need a couple of pairs to be on the safe side. To be honest with you, even 1 normally does that. Please understand what happens. This is your vertical asymptote. This is your horizontal asymptote. So the graph on the left side should go like this or like this, but not both. And on the left side of your vertical asymptote, remember, this is your horizontal. Let me draw the horizontal asymptote as such. So this is the x-axis, also the horizontal asymptote. So the graph goes like this or like this. So how do you know that? You need one pair on each side. We already have this pair. Practically, this is good enough. On this side, just to be on the safe side, you can pick 1, any number that does the job. And normally you want to go with easy numbers. So take a look. If we pick -2, we get 2 times -2, -4, and 3 is -1. 1 over that is -1. If you plug in -1, -2 and 3 becomes +1, and that gives you 1. So we have these 2 pairs. Let's plot them. So clearly, over here is like that, over here is like that. So take a look at the graph of the function all put together. You have your horizontal asymptote, vertical asymptote, the 2 pairs that we got here, the y-intercept. There is no x-intercept, there's a hole here. All of the above, they go together, and they give you a perfect graph. Given the function f of x equals x plus 1 times x minus 5 over x minus 3, find the domain of f in interval notation. The denominator set it equal to 0, x becomes 3, and exclude that. That's as far as the domain is concerned. So negative infinity to 3 union 3 to infinity. Asymptotes, the vertical asymptote is very simple. Denominator equal to 0, x equals 3. Then we have either horizontal asymptote or oblique asymptote, or maybe none of them. So we can look at the numerator and notice that the degree is true. If we do rewrite that, the degree is larger than the degree of the denominator by precisely 1. It results in a slant or oblique asymptote. So you have to divide the top by the bottom. So if we multiply them through, we get x squared minus 4x minus 5. If we divide by it, we get x minus 1 minus 8 over x minus 3. I'm assuming everybody can do all of this. This is either long division or synthetic division. This is your remainder. So this part, y equals this part, y equals mx plus b, y equals x minus 1 in this case, is the slant asymptote. Y equals x minus 1. And there is no hole. Hole is the result of a common factor between the top and the bottom. So VA short for vertical asymptote, x equals 3. HA short for horizontal asymptote, none. Slant or oblique asymptote, y equals x minus 1, there is no hole. So this is your vertical asymptote, and this is your oblique asymptote. You can pick a couple of pairs and graph them. Let's say x is 0, y becomes a negative 1, that's this one. And if x is 1, y becomes 0. So those are the two pairs you draw, and both are dashed lines because none of them is part of the graph. So in short, what happens is that the graph looks like this or looks like this on the left side. On the right side of your vertical asymptote goes like this or like that. Now, so let's continue with intercepts. So in order to find the intercept, set x equal to 0, find y, set y equal to 0, find x. So I hope you see that if you set y or f of x equal to 0, that means you're setting the numerator equal to 0. That's for x-intercept. You set the numerator equal to 0. So x is what? Negative 1. X is what? 5. Negative 1 means negative 1, 0. And this one means 5, 0. This is one of them. This is another one. We do have two x-intercepts. Y-intercept. Either this one or that one makes no difference. Perhaps if you go with this one, it's easier. Take a look. If you set x equal to 0, everything goes to 0 except the constant negative 5 and the constant negative 3. So you get negative 5 over negative 3, which is positive 5/3. So take a look. And I hope you realize that's really good enough. That pretty much gives you this part and this part. Those are the graphs, and you're done. Locate at least one point on each side near the vertical asymptote, sketch the graph. You really don't need any more points, but you're more than welcome to pick a point to the right of x equals 3. For example, plug in 4, and to the left of it, we already have 2. So this is the graph. You don't need to locate more, but it is absolutely up to you. And the graph looks like this. The function f of x equals x over x minus 2. We want to sketch a graph of f using technology to determine whether it's 1-to-1. At this point, you have enough practice, and the idea is that just plug it into a technology such as Desmos if you want to use a free calculator online, or a TI. The idea is just to do the math pretty fast. So the graph looks something like this. By the way, I hope you realize that, for example, you have a horizontal asymptote. See, this is 1, this is 1. So this is y equals 1. And you have a vertical asymptote, x minus 2 set it equal to 0, x equals 2. So that should be pretty clear. So you can draw that. In fact, let's just quickly do that so everybody can see. So those are the asymptotes that we see. And it is a one-to-one function. And the reason is very simple, because it passes horizontal line test. Because it passes a horizontal line test. This passes a vertical line test, it makes it a function. It passes a horizontal line test, therefore it's a one-to-one function. So perhaps we should really add this piece that says it passes both VLT and HLT, vertical line test as well as horizontal line test. Therefore, it makes it a one-to-one function, and we know how to find the inverse for a one-to-one function. Okay, so that's what we are going to do in this step. So first and foremost, we call f of x y, and now we interchange x and y. So this becomes x, this becomes y. And now we want to solve. Remember, right here we have the inverse, but we always solve for y. So we do the cross product here. So this becomes xy minus 2x equals y. If you take this here, becomes minus y, and this becomes 2x. So I'm going to quickly write that. So I can say minus y 2x, and that's how we get to this line. And we are going to divide both sides by x minus 1. This is the inverse, and we can easily graph that one. Okay, it's fairly simple. Going back to this, remember x equals 2 and y equals 1. Now notice x equals 1, y equals 2, because they are inverse functions, that's what's going to happen. Now, we want to find the domain of f. Look at f. X minus 2 set it equal to 0, x equals 2, and exclude that. Every number except 2, that is the domain. So negative infinity to 2, union 2 to infinity. Now, the rest of them, domain of f inverse, range of f inverse. Now, remember what happens in the case of inverse function. Domain of one becomes range of the others. Because the domain of f is found, range of f inverse is the same thing. Notice that. Now, what is domain of f inverse? Go to f inverse, x minus 1 equal to 0, x equals 1, exclude that. So all real numbers except 1. So that means negative infinity to 1, union 1 to infinity. And domain of f inverse is found, so is the range of f. I hope you realize this happens due to the relationship between the two functions that are one-to-one. We want to solve the following inequality, graph the solution set, and write it in interval notation, x squared minus 3x minus 18 over x plus 2 larger than or equal to 0. Anytime you have a non-linear inequality, to solve that, the fastest and easiest way to factor the top and the bottom first. The top becomes x plus 3 times x minus 6 times over x plus 2. And then write all the important parts. That means what makes it 0, what makes it undefined. Negative 3 and positive 6 are the zeros. Negative 2 makes this undefined. So you have to go with the number line and put them in order. It doesn't have to be perfect, but in order. So x, and I'm going to give it a name f of x. We're going to call this f of x. At -3, this expression, we called it f of x is 0. At -2 is undefined. At +6, it's 0. And now, basically, we do a test point. If you pick a point to the left of -3, for example, -4, and it's easier to observe it here. You can do it here, but it's easier to observe it here. -4 and 3, that's negative. -4 and -6 is negative. -4 and 2 is negative. So let me write that. I want to make sure we understand that we are choosing a TP, short for test point, -4, and we are plugging in. So this is negative, this is negative, this is a negative times negative over negative is also negative. You can do the rest in the same manner. If none of them has a degree even, then it alternates. So this becomes negative and then they alternate, negative, positive, negative, positive. If you have any doubts, pick another test point. For example, between these two, pick up -2.5. Between these two, of course, the easiest point would be 0, right? TP, short for test point, and check it out. Again, let's just, in case between these two, like -2.5, between these two, the best choice and easiest choice would be 0. Over here, any number larger than 6 will do the job. So what happens is we go back to the original one. We want greater than or equal to 0. So anywhere you see positive is the answer. So from here to here and from here on. Now, pay attention to the way we are going to write the answer. Is -2 included? No. Why not? Because it's in the denominator, makes it undefined. Is -3 included? Yes. Is +6 included? Yes. This is a graph on a number line, and this is in the form of interval form. Now, what I want to add as a note here, what you did here as a sine graph. So this was a sine graph, everybody. Even if I had x plus 3 times x minus 6 times x plus 2 larger than or equal to 0, less than 0, less than or equal to 0, all of the above, we use the same sine graph. The difference is, if you look at this one, the difference is that because it's a 0, even -2 is fine, and we use bracket on -2. And that's the idea I want you to pay attention to. So my point is, if you change this inequality to anything, you still use the same sine graph. If you put the x plus 2 at top, you still use the same sine graph. The endpoints may change, and you want to be careful with that. Now, we want to graph polynomials using zeros and end behavior. So let's remind everybody of what we have learned as far as the end behavior of a polynomial function. So the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n, x to the power of n plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0. This whole function ultimately looks like this. A sub n, x to the power of n. Ultimately, that's the concept of an end behavior. So take a look at what happens when we have a degree even. That means x squared, x to the power of 4, so on and so forth. So either a sub n, the leading coefficient, is positive, and therefore it looks like x squared. That means we are in the first and second quadrant as the end behavior, meaning as x approaches negative infinity in this side, the f of x goes to positive infinity. On this side, x goes to infinity, f of x goes to also infinity. However, if a sub n is negative, the leading coefficient is negative, remember, it opens down, so we are in the third and fourth quadrant. Third and fourth quadrant. If we are dealing with x cubed, that means anything that has the odd degree here, doesn't have to be 3, then when the a sub n, the leading term, is positive, we are in the first and third quadrant. If it's negative, we are in the second and fourth quadrant. This is just to refresh your memory about the end behavior. I hope everybody is comfortable with that. And the idea of a multiplicity, as the function crosses x minus c to the power of m, what happens? It depends whether m is odd or even. So when it's odd, it crosses the x-axis. It goes through the x-axis. When it's even, it just doesn't cross, whether the multiplicity is 2 or 4 or you name it, as long as it's even. So using that, we can see how the graph looks like. By the way, the higher the multiplicity, the flatter the curve is at the 0. The sum of the multiplicities is the degree of the polynomial function. So we are looking at this one, and the main thing is the first term. This will ultimately look like x cubed, and we should know that. We can do the factoring here. It looks like this. This is x squared times x minus 5 minus x minus 5. So you can factor x minus 5, which becomes x squared minus 1. And this is the factored form. And therefore, we have the x-intercepts at x equals -1, that means -1, 0. At x equals +1, that means 1, 0. At x equals 5, that means 5, 0. And by the way, it's easier to go to this one. If x is 0, y is 5, 0, 5. So let's look at the x-intercepts. Those are the x-intercepts. And let's look at the y-intercept, 0, 5. And by the way, and none of the x-intercept has a multiplicity. And so the end behavior looks like x cubed, meaning x goes to negative infinity, so does y, or f of x. X goes to infinity, so does y, or f of x. So that means really the end behavior puts you here and here, everybody. So if you graph and you start from here, you have to hit the first x-intercept, you have to come back up and go back down in this format. This has got to do with following the end behavior and the behavior near an x-intercept. Now this may, give you better idea as to the points that are crossing points. So that's why I gave you this graph also. All right, we're going to repeat this with a different function. First of all, we have the x-intercept at x equals 2 and at x equals -3/2. So this results in 2, 0. This results in -3/2, 0. This has multiplicity 2. This has multiplicity 1. And as far as the y-intercept is concerned, replace the x with 0. You get negative 2 squared, which is 4. You get 3, and that the product is 12. So we have x-intercepts at 2, 0, multiplicity 2. At negative 3, I have 0, multiplicity 1. So those are the two pairs. And here's the notation that is used in calculus, meaning it can't cross that. When we get there, when we draw the graph, however we have to graph it, it can't cross. We will get to that in a moment. The y-intercept was discussed. Replace the x with 0, you get negative 2 squared, which is positive 4, and times 3 is 12. So we have that. The end behavior is just like the previous page, because I hope you realize it's x cubed, degrees 3, or you can add up these two if you will. And we have the same end behavior as it was mentioned. So we are in the first quadrant and the third quadrant. So as you come on down and you hit your x-axis, you can't cross. You have to go back up. That's the idea. Hit it, go back up. You have your y-intercept, and you have to come back down to hit the next x-intercept somehow. And the graph looks like that. Again, I'm giving you this because it might give you a little bit more details. What is the least possible degree of the polynomial? Write an equation for it. Well, there is 1 term, 2, and 3 terms. Minimum of 3 plus 1, 4, because there are 3 terms. So how do we come up with f of x? We write f of x equals some sort of a leading coefficient such as a. This one is located at negative 3. So x plus 3. This x-intercept is located at negative 2. So x plus 2. This one is located at positive 1. So x minus 1. And this crosses multiplicity 1, but this one doesn't. So multiplicity 2, this one. So a times x plus 3 times x plus 2 times x minus 1 quantity squared. Why is this going with the exponent 2? Because it doesn't cross. Pay attention to that one. In other words, the notation that I showed you in the previous page. We also see the y-intercept is located at 0, 3. Plug in, replace the y with 3, x with 0. So every x here, we replace it with 0. And f of x or y, we replace it with 3. So this is 3, this is 0 plus 3 is 3, this is 2 minus 1 squared. And I hope you realize this is 1 because it gets squared. So 6a and a becomes 1/2. A becomes 1/2. And this is your final answer. If you want to write them in this format, it's absolutely perfect. If they ask you to find the final answer, you can multiply them through, but you don't have to, unless you're asked. This is a better format as far as I'm concerned. But whatever they ask you, you want to follow the instruction. Find the degree, leading coefficients, and the maximum number of real zeros of this polynomial. Also describe the end behavior. So the long run behavior, of course. And so let's quickly do that. All we have to do, rewrite that in descending order. It helps. I'm hoping everybody is having an easy time with this. So that means the n is 7. This is the leading term. This is the leading coefficient. So degree is 7 and leading coefficient is 4. So because the degree is 7, you basically go back to x cubed and how it looks like, because this is 4. Again, it's 7, you have to go to x cubed or negative x cubed. Because the leading coefficient is positive, you go to x cubed. And as far as the maximum number of zeros, whatever the degree is, 7. So maximum number of real zeros is 7. Same as degree. The multiplicity counts, by the way. X goes to negative infinity, so does y. X goes to infinity, so does y. This is the end behavior, just like y equals x cubed.